SwayamPrabha. Digital India. Educated India.
Good morning. See, today we will be discussing the physics behind another experiment which is titled as static lateral directional stability test. That is static, I am not talking about dynamic, static. The important thing is lateral directional stability test. If you see the key terms, when I talk about static stability, you all understand. Static stability means if a body is in equilibrium, if there is a disturbance about the equilibrium, and if it has a tendency to come back to the initial equilibrium, or initial tendency is the critical word, right? Then you say statically stable, right? So you can have for a longitudinal case, suppose it is going at an angle of attack 2 degrees, because of some upward gust, the angle becomes 3 degrees, let's say. So it should be able to automatically generate an initial tendency or initial pitching moment, which will try to come back to the 2 degree. If it has, we say it is statically stable. That is a longitudinal case. For lateral case, what is the lateral motion? If I am moving the airplane like this, which one is lateral motion? Roll, right? So what is the understanding when I talk about static stability in lateral direction? That means if there is a disturbance which changes the bank angle, it should automatically generate an initial moment which will try to bring it back. Then only it is statically stable in lateral mode, right? But how does it generate? Question is this. For longitudinal case, if there is a disturbance, there is a horizontal tail here, which gives you the moment, right? But for lateral case, you do not have any such which can give you that moment. So what is the mechanism? What happens? Just watch me appropriately. If the airplane is going like this, and if there is a bank, the moment there is a bank disturbance, what the airplane will do? Start side slipping, right? As it side slips, since there is a vertical tail will experience the force in this direction. So that will give you a rolling moment. So for a positive beta, it should generate a negative rolling moment. So we say CL beta should be less than 0 for lateral static stability. Is this part clear? So we say CL beta should be less than 0 for lateral static stability. Okay. Now, who does the active control on the roll? For example, the airplane is going like this. You actually want to roll the airplane like this. So we always say when right wing going down, that rolling moment is convention wise it is positive. Right wing going down is positive. Left wing going down is negative, right? So suppose I want to change the bank angle of the airplane from 0 to 5 degree. So which control surface I should deflect? Is it it is the aileron, right? So next question will come, how much per unit deflection of aileron will produce a rolling moment, right? And that derivative is known as CL delta A. This is called aileron control derivative. Right? Okay. Now you can imagine if the airplane is like this and it is rolling like this. So what is happening? If it rolls like this, the right wing, watch out a right wing. So right wing is going down. That means right wing is seeing relatively air speed perpendicular to that as it moves like this. That is, if I draw it here, if this airplane this wing goes down. That means at each point you could see there, what will the velocity here at a distance r from the center? If it is rotating at a omega, let us say, it will be omega r. So that much induced velocity it will see, and that velocity component will go on increasing because r is increasing. Correct? So there is an additional vertical velocity of air the wing will see. It means the right wing will see additional positive angle of attack. Correct? So here, right wing or whatever wing is going down here, so it will experience a force in this direction. Correct? Similar thing will happen in the opposite direction here. So it will experience a in this direction. What this will do? This will try to counter whatever way you wanted to rotate it. No issues? Now, if you see here, this whatever angle of attack is being induced at a distance r will be what? Will be whatever angular rate, let's say it is rotating with angular rate of, I say p, then into r by v, whatever forward speed was there, approximately that will be the angle of attack seen by the wing at a distance r. Correct? So I could see that this force, that delta L, will be proportional to P. Correct? So the moment also will be, rolling moment L will also be proportional to P. No objection? Now this moment will be termed as what? A stiffness or a damping? Damping, because you all know that for a second order type of modeling, so this is Cx dot, this is proportional to the rate, and that C is the damping constant, right? So you have a damping also in roll, and that rolling moment is represented as CLP, which you know all very well. This is dPb by 2U. This is P is non-dimensionalized by multiplying by B by 2U, and that you know from other lectures, whatever in other courses we have done. Okay. So this is the lateral part. Okay. Now, if I come to directional part, so let me write this. We have identified CL beta, we have identified CL delta A, we have identified CLP. Also, before I come to directional, you should also understand that if this is the rudder here, and let's say this is the center line of the airplane. So if I deflect the rudder, what it will do? Suppose let us say this is the rudder over the fuselage, right? If I deflect like this, what this will do? It will generate a force in this direction, because moving in forward direction. This force will do what? One is it will give a yawing moment, and there is what? Because this force is somewhere in the center here, and there is a distance from the center line of the fuselage, so this will also give a rolling moment. So you can use a rudder rather to generate rolling moment. We denote this using notation CL delta R. So what is the meaning of these derivatives? These are all partial derivatives. CL beta means dCl by d beta. CL delta means dCl by d delta A, and rest you know. Why we are writing it like this? Because we are assuming that we are working in a linear domain, right? And partial derivative means what? What is the meaning of dCl by d beta? What is the change in CL per unit change in beta holding other constant? That is a partial derivative. So I can use this under the linear approximation. CL I can expand as CL beta into beta plus CL P into PB by 2U plus CL delta A into delta A plus CL delta R into delta R. Are you familiar with this expansion? Sure? Somebody may ask, there could be a rolling moment because of yaw rate, right? So if that is you are considering, then you have to write CLR into RB by 2U. Right? So this is how I expand the CL for mathematical treatment using CL beta, CLP, CL delta A, CL delta R, and CLR. And these derivatives are called aerodynamic derivatives. They are called non-dimensional aerodynamic derivatives. Right? And what is the use of this? If I know the values of CL beta, CLP, CL delta A, all these non-dimensional aerodynamic derivatives, then I can postulate a model of CL mathematically. And if I know what is the value of beta, what is the value of P, delta A, etc., I can estimate how much rolling moment coefficient the airplane is experiencing. Right? Then you can write the equations of motion, etc., etc. Right? So it is important that we should know what are the. It is important to know what are the values of this. We estimate these values through analytical method, through wind tunnel testing, but finally we do flight test and see whether how accurate are those estimates, and then we go for our further analysis. Right. So this is a lateral part, and we will do something to see how much you can estimate through the experiment. Second part, when I come for directional, what is the directional case? We know longitudinal is about y-axis, right? And lateral is rolling about x-axis, and directional is about z-axis. So what is the convention for directional case? Right wing going back is positive. So the yawing moment coefficient will be positive if right wing is going back. Okay. So and Cn is the yawing moment coefficient, and you all know how they are defined. This is yawing moment, non-dimensionalized with half rho v square s into b. B is the span. These are our usual definition. Now, once you know the role, say Cl was function of P, R, beta, delta A, and delta R. Since we wrote Cl equal to CLP into PB by 2U1 or 2U plus CLR into RB by 2U plus CL beta into beta plus CL delta A into delta A plus CL delta R into delta R. Once you are confident about this, now help me, how do I expand Cn? Cn should be what? Same. This is Cn P into PV by 2U plus Cn R into RB by 2U Mechanically, I can write this, no issues, right? But let us see whether we understand these derivatives or not. Okay? Let me pick first Cn beta. What is Cn beta? What is Cn beta? Yes. Anything you associate more with Cn beta? For static stability in longitudinal case, what was the condition? Cm alpha should be less than 0, right? So what is the condition for directional case to be stable statically? Cn beta should be greater than 0, right? The condition is Cn beta should be greater than 0 for for directional static stability. If I recall, how do I visualize this? See, for example, again, you see, suppose this is the vertical tail, okay? This is the vertical tail, and the airplane was going like this. Airplane should go in the configuration beta equal to 0. Suppose there is a wind coming like this, right? So there is a positive beta now, okay? So to make the beta 0, what will happen? What the airplane has to do? Turn into the wind, So what will become? Beta will become 0. So it should have a natural tendency or initial tendency to come back to the equilibrium. To have that, the right wing has to go back. So for a positive beta, Cn should be positive. So Cn beta should be greater than 0. Clear? And if you recall earlier lectures, if I plot Cn versus beta, it should be something like this. The slope should be positive. dCn by d beta should be equal to 0 for directional case. For longitudinal case, if I draw Cm versus alpha, I want it should be, slope should be negative, right? So we say dCm by d alpha should be less than this. So we have understood what is, or you have recalled, in fact, we have done all this thing earlier. The Cn beta should be greater than 0. Now let me pick, say, Cn delta R. Okay, let us see. What should be the sign of Cn delta R? Okay. What is Cn delta R? Cn delta R is coming because of rudder deflection. Yawing moment because of rudder deflection being non-dimensional. So now let us again come back here. Suppose we define, which is as per the convention, looking from the top, I am moving forward. If rudder goes like this towards left, it is a positive rudder deflection. Clear? Towards left, looking from the top is a positive rudder deflection. So if there is a positive rudder deflection, the side force on the tail will act in which direction? Moving forward. So it will come towards this, right? Yes or no?
Yes, sir.
This will give what type of yawing moment? CG is in the front.
Negative.
Negative. So what is the sign of Cn delta R? Negative. Okay. Very good. So Cn delta R sign should be less than 0. So other signs you can find out, or you can refer my earlier lectures. With this understanding, now we will be conducting some experiments to estimate these derivatives. Also, we will try to see through such tests what are the derivatives we can find out in a approximate manner, or what are the relationship among the motion variable, which should satisfy us that whatever six-dog model we follow conventionally, they are accurate or they are appropriate.